Good evening, everyone. For those who don't know me, my name is Will Galloway, and I'm the host for this evening. And I co-chair the lecture committee at the Department of Architectural Science at Ryerson University with Professor Terry Peters. So my main task this evening really is just to welcome everyone. So I will simply do that and welcome you all coming from Toronto and around the world to the Department of Architectural Science and also to this lecture series. So before we begin, I thought I would just briefly describe the theme of this series. And the speaker tonight, Léon Spikker, will be the first for this year. And the theme is very simply disruptions. And this is a very easy word. It allows all kinds of points of view, which is why we picked it. However, the point of view from which we are using it is really a reaction to all of the ways that we as individuals, as universities, as professionals, and even as countries responded to this we're now into the third year of this crisis from the COVID-19 pandemic. And one of the things that this crisis has revealed is a huge number of questions and issues that architects and everyone involved in the building industry are now being asked to respond to. And so part of the way that we're responding to that is to think about what kind of disruptions do we need and really how do we engage. And so that's really the source of everything that we're going to talk about. And we're very lucky to have three guests this year who will each address that in their own way. So before we introduce Léon, I wanted to give my thanks in two ways. First of all, I wanted to thank our sponsors for this lecture series, including the Ontario Association of Architects and the Royal Architectural Institute of Canada. And secondly, I would like to read the Land Acknowledgement. So as you all know, Ryerson sits on lands that are now known as Toronto. And these lands have been inhabited for millennia by many Indigenous nations and peoples. And it has now become our tradition to begin our meetings with a land acknowledgement, which not only recognizes the enduring presence and resilience of Indigenous people in our area, but is also a reminder that we are all accountable to these relationships. Toronto is in the dish with one spoon territory. The dish with one spoon is a treaty between the Anishinaabe, Mississaugas, and the Haudenosaunee that binds them to share the territory and protect the land. Subsequent Indigenous nations and peoples, including Europeans and newcomers, have been invited into this treaty in the spirit of peace, friendship, and respect. And it is in exactly this spirit and on behalf of our university that I welcome you all to Ryerson, to our department, and on behalf of the faculty that I welcome you all. So there's one more person that I would like to welcome, and that is my co-chair, Terry Peters, who will give us a brief overview about how we're going to work through this evening. So I give the floor to you, Terry.
Thanks, Will. So my name is Terry Peters. I'm an assistant professor in the Department of Architectural Science and co-chair along with Will Galloway in the DAS lecture committee this year. So tonight's lecture is by Léon Spikker, and the title of his talk is Computational Design in Practice, from Robotic Craftsmanship to Affordable Housing. And before we introduce the speaker, I'd like to give a brief outline of tonight's event. To start with, Léon will give a lecture of around 45 minutes, and then we'll have questions at the end. So I'd like to make sure the audience knows to write their questions in the Q&A rather than in the chat. And we will have questions at the end, and we'll be able to go through the questions that are in the Q&A. After Leon's lecture, I will turn the podium over to one of our student committee members, Sadberk Agma, and together we will coordinate questions from the audience. And now I'd like to ask one of our student committee members, Marwa Al-Sakar, to introduce this evening's speaker.
Great, thank you. So on behalf of the students, faculty, and staff at the Department of Architectural Science, it is my pleasure to introduce this evening's speaker. So Léon Spikker is a Dutch computational designer with a background in industrial design and architecture. As a co-founder of the firm Robotic, which is short for Robotics, Architecture, and Production, and the 3D printing software company Land Technologies, he has been at the forefront of bringing both digital design and robotic fabrication together into the building practice. From seeing the current conditions and outcomes brought forth by the architectural industry, Léon is more interested in challenging the conventional ways of design by using tools and materials that are already available to us to create a more durable, efficient, and beautiful architecture, all while keeping sustainability at the forefront. He is also working with Sustainable Home Builder in the middle of our streets to apply these techniques to affordable housing and address the shortage that is currently in the Netherlands. Within the team, Léon leads the digital development of 3 key technologies: customer-facing housing configurations, design for manufacturing and assembly infrastructure, and flexible factory process. Through a couple of projects, Léon will show us how techniques such as computational design and digital fabrication are necessary today and for the future of our building industry. We thank you, Léon, for joining us today. It's an honor to welcome you here. Thank you.
Perfect. So, yeah, welcome to my talk. It's a bit different than what we've planned. So first, thanks for having me, of course, and thanks to the organization and thanks to Will as well. I've known Will for a while. The image you see on the background here is a project we did together for a pop-up restaurant in Tokyo already 4 or 5 years ago. So it's been a while since I've seen him in person. And he asked me to talk to you guys about some new developments in architecture and construction, specifically in design and fabrication. So I also want to thank everybody who's taken their time to come to this lecture. Here it's a little bit past midnight, but for you it must be around dinner time. So yeah, it's okay if you eat during this lecture. It's one of the nice things about remote. So I can't really beat that introduction, so I'll keep it quite short. You're only seeing my face, but that's me there on the left. Pretty serious picture. So I'm a computational designer, an architect. I'm fascinated with design methods, materials, manufacturing. Really like to be in workshops in that way. I have a background in industrial design and completed masters in architecture at the TU Delft because I didn't want to work on mass-produced goods all my life. Graduated there in 2014, and I saw it has a bit of a similar focus as you guys have, so quite a technical school. Today I saw on Instagram that you guys are doing something with these winter stations, so I know there's some good things happening over there. And what I hope to do with the talk is to give you a little taste of the possibilities that computational design and digital fabrication, these two methods, can bring to architecture, but also to students or people already in their working career. I'll do that in 2 parts. I'll start with my work at Studio Rab, and I'll end with my work at Moos, or in the middle of our street. So I'll just kick it off right there. Okay, so Studio Rab, I founded that in 2014 together with 2 fellow students at the time, Wessel van Berendonk and Lucas ter Hal. And we did that because during our studies, we developed all kinds of tools and technologies that we were afraid to lose the moment we would go into the workplace. So starting as an intern or a junior architect, we didn't really have confidence that we would get the chance to work with those. We started in the middle of the economic crisis, so we started in a maker space in the Innovation Dock in Rotterdam. Quite a nice place to start out, but well, in that recession, it was really the choice either to work for free at a firm or work for ourselves and not earn a lot of money. So it wasn't that difficult, but it was not such a difficult choice. But the beginning was quite tough, starting out with a terribly old borrowed robot, doing a lot of manufacturing jobs actually to earn money and trying to develop our own style in the meantime. Excuse me. So in a couple of years, we built that into what is now considered one of the leading innovative firms in Holland, where design, research and development, and manufacturing are actually happening in-house. And that has won some nice awards in the past years as well. So what you see in this picture is the workshop. Has a couple of robotic arms, has a lot of prototypes, but actually also some production going on, with the office in the top left and the storage in the top right. So it kind of shows the emphasis on making and prototyping. And even though I've moved on to new things 2 years ago, I still think these guys are really doing great work. And I would recommend anyone to check out their stuff a bit later on. Or if you're interested in this, doing an internship or working there, to get in touch with them. So let's run through some of the projects to show you what computational design and robotic fabrication can do. The first project is the Skilled in Office. This is a project we did for the Port of Rotterdam Authority. So this is the first project we actually ever did. Sorry, some dry air here. Where the tenant wanted an indoor climatized office space with an innovative look. So it was the perfect brief for us as a young studio to start out. The design and fabrication had to be tied into each other. This is sort of the dogma that we worked within, where the roof is generated from a shell structure and then rationalized and brought back into panels that could be milled with a robotic arm. See that here in the video. So really the structure and the material go hand in hand here. So this the structure is generated using RhinoVolt. It's a plugin from the ETH in Zurich to create compression-only volts. And the system relies on the traditional finger joint for improving structural performance and easy assembly. We produced it ourselves with another second-hand robotic arm that was suitable for milling. And we milled about 350 unique panels that together create this load-bearing structure where the veneer of the wood is aligned with the highest resistance to stress. Excuse me. So that's also how we aligned the panels that we made within the stock material that we bought. So all of these things were done computationally directly from a parametric model of that volt. It took us a couple of months to manufacture and then assemble into this domed structure. And the result is really quite a small building, but for us, it was the first project in which we could actually prove that there's a huge potential in this in combining designing and making into one firm, and also bringing manufacturing forward into the design process. So taking these constraints and these material properties into account when designing. So not leaving them as an afterthought. So this is a project that we did for the Port of Rotterdam Authority, and they had another project later on. And this really showed to us that these digital tools are not just nice because they have an undo button or it's easy to make some changes in, but also that these algorithms can be applied to new cases with relative ease. So what you see here is another project for the Port of Rotterdam that unfortunately ended in the sketch phase, but we could easily whip up using the same algorithm. So it showed us that there's value in creating a sort of toolbox of codes and of methods to design and produce. So a second project that we did in wood is the circular experience for Avian Emerald Bank in Amsterdam. They built themselves a pavilion next to their huge headquarters that you see in the back there to sort of boost developments in circularity, show that their bank is taking that theme quite seriously. It's called Circle. It's on the Malerplein in Amsterdam. So if you're ever there, you can come and visit it. But they came to us to design an entrance to their art gallery and meeting spaces. So we went looking for a good way to approach that, and we found that during the making of their load-bearing structure, there was actually a lot of waste material lying around. So it was left at the lumber yard, but it was marked as trash and had quite a negative effect on the circularity score of the project. So we thought it would be nice to use that larch and pine in the cladding of this project. So we devised a system that consists of traditional detailing, but not with finger joints, but with dowels. So without glue or screws, and actually just with wood and just a post-tensioning rod to keep these panels together. Together, these panels would form a balustrade and wall cladding that would cover the gallery's entrance, and we would use the handrail to influence the parametric design of the wall cladding. So for us, this was really a way of pushing our control of robotic manufacturing to the limit. So we went all out and devised a robotic fabrication process where the robotic arm as a craftsman handles these small battens of wood and goes through a couple of actions and then positions them on the right spot within this segment. So you can see that process here. It involves around 6 steps with different pieces of larch and pine, either 50 or 30 centimeters long, where they're drilled from top and bottom, they're sawn to length, dowels are introduced into them, and they're then placed on the right spot. So the tools that you see here were also hand-built by us, mostly because this process isn't used in the industry at all, also because it's pretty laborious. But you can see time-lapse here. These processes normally took about a day to complete. So the segments that you see in the end here are stringed together. and put into the gallery space near the entrance. And what I personally really like about this project is that it shows that waste as a material for building or circularity principles don't have to be boring or ugly, but that they can be used in pretty inspiring and aesthetic ways. So it's a unique piece of architectural cladding, which really wouldn't be possible without the tight integration of computational design and robotics. So we, on such a small project, we really pushed what could be done with such materials, but we were ready to move on to some other materials as well. People really knew us as the guys who only work in wood. So when BPD Development approached us for a project, we didn't hesitate and hop on it. There's a project called New Delft Blue, where we were asked to design a couple of archways into a communal garden of a new residential complex. And Delft is a historic town in the west of the Netherlands, and it's known for its Delft blue pottery, as well as the technical university where we had all graduated. And we decided to reinterpret those in the those two factors in the design. And we started with the structure of the iconic Delft blue plate, which contains a decorative frame, often natural or floral patterns, and then an idyllic scene in the center. And within the project, the gates actually already framed the idyllic scene, which is the lush courtyard in the middle. So what we wanted to do was use the arch as a decorative frame for that, to guide the viewers inward, where we would make ceramic panels, 3D print them from clay with our robotic arms to create a unique gate on every side of the building block. So here you can see what that looked like. So it's a custom extruder that prints panels of about 30 by 50 centimeters high. And all of these tiles could be produced uniquely. So it doesn't really matter whether with 3D printing you print 1,000 times the same panel or 1,000 times a unique panel. The production time is pretty much the same. It's just in the robotic control and the design where you have to make that differentiation. So what we wanted to do is use that cheap form, or that the way that we can achieve that form to paint this floral pattern. So together with Royal Tichelaar, a very famous ceramics company in Holland, almost one of the oldest companies here, we developed a runny glaze that we could put on the tiles and that would run into the valleys in between these hills that you see. And we wanted to do that to create a sort of halftone effect between blues and whites. And so we wouldn't have to hand paint the tiles to achieve this differentiation, but the form and the runny glaze would force this effect. And you can see that in these early prototypes that we made, that the effect is quite visible and striking, and that there is a nice accentuation of the print layer as well. So there's multiple layers of expression in it. For the overall design of the arches, we went with the floral patterns from Delft Blue, as well as some cues from the nearby waterways and canals that Delft is very well known for. And it's just used to accentuate the entrance to these shared gardens. Here you see a detail shot of how these panels would be lined up and how each of them unique contribute to this overall image. So here's an outside shot of that building block and the small archways and how it looked in the end. So from that project on, we realized that we didn't just want to do aesthetically pleasing additions to existing buildings, and I was quite enthusiastic when we were asked to work on bus stops. So this isn't really the thing that most architects would consider challenging or interesting, but with my background in industrial design, I thought that designing products for public space is actually a pretty neat thing to do. And what we wanted to do was look at how we could contribute to society a bit more with the tools that we had developed. So the assignment was focused on turning the generic bus stop in the Netherlands, which is quite a depressing place, into something more comfortable and large enough for the amount of users that actually use it. So bus stops are maintained by, or placed and maintained by, advertisement companies, and they're not really interested in that. We found out that the physical infrastructure has a really big effect on bus usage, and that these low quality bus stops were actually keeping people out of buses and in their cars, where the province wanted us to do that the other way around, so get them out of their cars and into the buses. So they asked us to look into a more suitable solution that would be in between the stops that were there at the moment and the really large scale comfortable bus transfer stations that exist in central parts of large cities. And this is where we started thinking about the idea of a family of bus stops. So a design system that could adapt to all kinds of positions. So rural, urban, suburban, anywhere in between, where services and amenities could be adapted to that specific location. Rural stops would get electric bicycle charging or package lockers, while urban stops would be more compact, but had more information on what could be done in the surrounding environment, for example. We had a good test case on a plot near the Erasmus University that saw really large peaks in the morning and afternoon, but in the middle of the day, almost nothing happened. And this design system would adapt to that narrow plot and still cover about 350 people per hour. So really big change. And we made a couple of modular and adaptable designs that could be made using robotic manufacturing methods. And they could be produced in different sizes. So for these different sites and containing these different amenities and services. But unfortunately, when that bus stop got moved because the contract with the bus company was ended and the local government changed, the project fell through, but it put us on an interesting path because it gave us, it brought us another project, which is the last one I'll show from my period at the RAP, but which is the 3D concrete printed Abri, which is also a sort of bus stop, but this time for the city of Rotterdam, so not for the province of South Holland. And it wasn't about buses, but about water taxis. And they sort of stitched together the two sides of Rotterdam, so the north and the south. Rotterdam is cut by a river. And they also wanted to promote the use of that way of transport. And during that time, we had just started working with Brel, which is a large concrete manufacturer that was starting to use an experiment with 3D concrete printing. We had been working with them to develop some software for them to do that. They had seen our project with robotics, like Circular Experience and Scaled In, and had asked us to make some first software tools for them. And we wanted to apply this new technology in a project, because similar to the ceramic 3D printing, you could make unique objects at pretty much the same cost as you would a mass-produced one. So then the design for the water taxi was a model that we could use to generate unique coverings for every stop from one single parametric model, where it would always cover plenty of space for the amount of people that will wait on that spot. The design was rather straightforward, so a cantilevering concrete shell. But in 3D printed concrete, that can provide quite a challenge, because it's still almost impossible to incorporate rebar into 3D printed concrete. So it's something that hasn't really been solved yet. But we circumvented that problem by designing a post-tensioned hollow concrete shell that would consist of multiple 3D printed parts and held together by steel tension cables that you see in that video there. So it would sort of pull together that structure a little bit like the tendons in your hand. It was quite an experimental design, and because of its public use, also had to take into account all kinds of severe abuse and the notorious soccer hooligans we have in Rotterdam. So we had to make a prototype that could withstand all of these influences. Here you can see the robotic arm that's printing the one of the bottom parts of the shell. We had to revise the design quite a couple of times, because the production capabilities of these machines and of this concrete were really limited still at that moment. But what you can see here is that there are hollow channels through which these tension cables would run. So these are all the elements that you need to produce that mock-up, which was then assembled in a week or so. So this is the first prototype we made for it. And we actually discovered that even though the printing of it was quite straightforward, it needed extreme amounts of scaffolding and tooling to keep it in place before it was post-tensioned. So the temporary bracing was really something we hadn't foreseen at the beginning of that project, and unfortunately, we tensioned this prototype after adding this large steel plate at the top, and during the tests, the entire prototype exploded because of the tensions that apparently weren't calculated properly. And it showed us that this technique was actually a little bit too early to put into the public space. But what it did, these last two projects, so these projects for the public space, and we were thinking about families of objects that would come from a central parametric design or a design system, was that there were more ways of applying computational design and digital fabrication than just doing decorative coverings or developing these procedures ourselves. So kind of got me thinking, and halfway through 2020, I decided to quit at RAP, because I had worked on a design for a villa for 4 years, which was a beautiful chance to do and a beautiful project. But as as a millennial, I thought that working 4 years to house 4 people didn't really scratch my my itch to have an impact on our society in a positive way. So when I quit, I had some time to think and talk with people, and that's when I joined forces with In the Middle of Our Street to lead their digital design and technology developments. And this is the second part of the presentation, so I will try to run you through this. And so this is the other side of the spectrum of what computational design and digital fabrication can be applied to. So In the Middle of Our Street, MOS in short, is a modular housing company based in Amsterdam, and it was founded 2.5 years ago to provide a thorough, realistic solution to the housing shortage that exists in the Netherlands. We have about a million homes that we need to build in the next 10 years, I think. And what I hear all throughout the world, there's actually a similar problem. But we want to do this in a way where we actually reduce carbon emissions instead of adding to them, and not be so wasteful during construction. The focus of MOS is on affordable housing. So this is like the missing part of the Dutch housing market, where low and middle income families can rent apartments. And MOS tries to do that with a diverse set of floor plans, so that suit a diverse range of people. Currently, social housing is often designed with a standard 2-bedroom, 70 square meter apartment, which is too big for a lot of people who start out and too small for a lot of families. But since there's the waiting lists are so long, people just take it and then they will just use that extra room for storage or whatever. But it's a very inefficient way of clearing that waiting list. A second important aspect is that the design consists of a structural hybrid. So where you see a lot of, currently you see a lot of building systems that are only CLT or only timber. This actually uses a recycled, a concrete floor made from recycled cement in combination with cross-laminated timber walls. And the idea behind that is that the concrete floor actually solves a lot of issues in stability and acoustics, adds a bit of thermal comfort, but also that you can build these really, really quickly. And that often these projects are put in a plot where previously a 70 or 60-year-old building has been torn down, where a lot of waste concrete comes out of the project. So we try to bring those resources back into the project that comes in its place. A third aspect is that the way in which you build should be different from the way that we're doing it now. We're probably not going to solve these problems in the same way as we've been creating them. And this means that on the left, you see the traditional way of working with the client at the top and all of the subcontractors and producers on the bottom, which is a completely fragmented, divided value chain. So people are fighting with each other, and there's no shared responsibility. So with MOS, there's actually a shared responsibility over the end product. And the design team includes the production partners, as well as smaller subcontractors, as well as the regular attendants like the architects, advisors, and consultants. Also, this team is not a single-use thing. So we work with this team for at least 5 years. And so all of the projects that we will start in those 5 years will be done with that same team. So people are committed for a longer term, and it's done for the entire life cycle of the building. So that requires a different process. So to explain that, current building life cycle has two big cuts in it. One after design and engineering, where the general contractor takes over, and then one where the building is handed over to the client for use and maintenance. And what you see there is where those cuts are, that's where responsibilities end. And that's also where a lot of information is lost. So what we try to do is introduce a closed cycle, where using a modular building system, we can reuse the modules in new projects. And that gives us an incentive to design them in a way that they maintain their value for a longer time, but that they can also be taken apart easily, upgraded easily, and then reused easily in a new project. So this is not a 5 or 10 year vision, but this is something that will pay itself out to us in 30, 40, or 50 years. And to support this much more integral process, we have to augment it with a digital chain of solutions. I don't want to make it too complicated, but that makes it possible for partners and clients to maintain control over all of these different phases that we're going through, and to see where projects are across all of these phases. So you can see when a project will come back for disassembly, or whether it's in the use and maintenance phase, or whether a project is just in the design and engineering phase. So to talk about that design system for a bit, because that's the part I want to focus on in the bottom left. It spans the entire spectrum. So it's an architectural design system that contains staircases, elevators, walkways, balconies, installations, plumbing, facades, everything. And so the role of architects, engineers, and designers at MOS is really to develop this system in a way that it's attractive for other architects to apply. So it's a sort of white label system to introduce. And it goes from the smallest element, a faucet, to a complete building block or complex. And the idea behind it is that our building system will cover the part of the design that can be optimized relatively easily, and leaves the part where architectural expression and the individual character of the building, also for the local surroundings and the urban quality, are left to the specialist architect or local architect who knows what fits best in that situation. So if we're talking about this modular system, then what's that module? So every unit consists at least out of one module, which is the basic module, which contains a toilet, a kitchen, and a bathroom, and the entrance. And it's about 3.5 by 10 meters long. Additionally, there's a personal space, which is pretty much a void module that can be arranged by the users themselves. So it leaves a lot of space for personal interpretation. Together, these form a apartment. In this case, it's an M apartment, which consists out of 2 basic modules. So these modules together can form around 14 different floor plans that are divided into 3 or 4 different building types that can be served. And they serve in between 31 to 163 square meters. So you can see that a very wide range of floor plans can be realized in that way. And the topologies that we can realize in that with that same system is also also has a lot of variation in it. So you can have a row house on the left, so a single family house. You can have a single loaded corridor building, a tower, or a corridor or double loaded corridor building on the right. And it allows us to create blocks with a lot of variation, a lot of space for different target groups, different tenants. So a lot of diversity within a single block. So the mock-up that we built of this, you can see here. So it's a concrete floor with CLT structural system on top of it. And these free spaces allow for a lot of space on the inside. So because the kitchen that you see on the right is actually in the module that you're not standing in, it leaves the full 3.2 meters of free living space in the middle. And this is really something that's uncommon in modular homes. So the quality of living in these is quite high for a product that's designed for really social housing and middle income housing target group. So this mock-up, you can still, if you're in Amsterdam anytime soon, you can still see it. It's in Zaandam, just above Amsterdam. And you can see there's no facade on it because it's a white label housing solution. So the idea is that we as a company don't want to build 1 or 2 buildings in the coming 7 years, but we want architects to pick up this system, to design with it, and then have our partners manufacture it. We don't have one large factory, but we just have an assembly hall where we put together the parts that our partners manufacture. But then the question is, how do you manage the complexity of such a system? Like, how do you start that design process? So what we did is before we start a BIM design project with the local architect, there's actually a phase where our client can use a configurator to realize and capture their intent into. So they can actually play with the system themselves on their iPad or laptop to get a grasp of what this building system can do. And I think it shows what computational design and these design systems can do, is it can actually bring the complexity of such a system into the hands of a relatively untrained user. So here you see a recording I made this afternoon. So the app is now also being used by some of our clients, and we're adding a address in Amsterdam, can be any address in Holland actually, and it loads information from the government database for geomatics. So it's addresses and parcels. You can select the parcels that you want to build on or that you've bought, inspect some information about them, for example, zoning restrictions. And after you've done that, you can start thinking about what kind of buildings you want to put on top of it. So the tool has been built in the past year together with Matas Uberevisius of Bit by Bit Developers. He's a software developer that we worked with a lot also in my time at RAP. And we decided to build this ourselves because we didn't find a solution that actually fits modular housing. So there's a lot of design tools like these out there, but none of the solutions that come out really have a price in them that makes sense. So on the left, you can see that as you manufacture as you design and configure the building, the costs on the left side increase or decrease depending on what you're changing. So you can change where the entrance of the building is, how large it is. You can change what types of heads you want, so that the endings of the building. And what this really is a feasibility, like a technical and financial feasibility study for corporations, social housing corporations, and developers. That's available for free. So where normally an architect would take about a month or 2 months to develop such a plan, now these clients can try it out themselves and then come up with a very basic feasibility study to then continue into a design process within our within MOS, but then with the help of a local architect. So I'll skip this forward a little bit. So here we're adding some row houses. So it contains all of the typologies that the building system entails. There's not really any limitations to that. And we try to continuously update it as we make changes to the system. So it's never really outdated. You can change the type of plinth that you want in the building or the type of crown that you want on it. And all of the metrics that you see on the left change with it. So the building cost, the GFA and UFA ratios, the amount of units that you're realizing. And we believe that in that way, by putting these kinds of tools in the hands of the users, that we can lower the threshold of using these, and that it's also a way to reduce the complexity of the use of a system which would normally require experts to handle. So all of the complexity has been hidden on the back end, and we've reduced this building system into this sort of Lego-like configurator. So I think with that, playing with it for a little bit more, but I think with that, what I want to show you is that the range of what you can do with computational design and digital fabrication is really wide. So it can be a useful tool within a project to design a nice load-bearing structure or a wall cladding project. You can go all in and develop your own manufacturing technologies and go into 3D printing with clay or concrete, but that you can also use it to completely rethink the way in which you develop housing for low and middle income families. So I do think that it's a really interesting time to be working in this field and to have these tools available to you. So I'm quite curious to hear what your findings are. And if you're listening to this later, of course, you can also get in touch later by sending me an email or reaching out on social media or something. So thank you very much.
Thank you for your lecture. That was really interesting. I hope people can put their questions in the Q&A because I know you covered a lot of really interesting projects and a range of different kinds of explorations of computational design and fabrication.
Yeah, sorry, it gave me a really dry throat there in the beginning. I was like, oh, I'm not used to presenting anymore.
It was great. Sagma, do you want to read the first question? Can you see the Q&A? Yeah.
So one of the attendees is asking, so Oliver Alto, the Finnish architect, emphasizes on tapping into our subconscious through haptic process of drawing and crafting with materials. What is your take on the value of using hand and haptic methods versus with robotics and computational design in the process of designing, as well as what is your process of designing in the realm of computational design and robotics?
Yeah, cool question. So actually, for me personally, I still sketch a lot. I think the tools that you use really, they can really limit you, definitely if you're not very experienced with them yet. So if you're just starting up Rhino or SketchUp, then you only get little blocks showing up in your project. So I think in that sense, the tools with the lowest, with the least constraints are quite good for ideation. About the haptic part, so I didn't really understand that process. Sorry, I couldn't see the question, but do they mean sort of reading your mind, or do they mean haptic feedback to control the robot?
I think they were just trying to compare in a way. That's sort of what Alto does, and what's kind of your take in the. I'm not actually sure what they mean by haptic methods on that note, actually.
Yeah, I mean, you do see some experiments where people are using haptic feedback devices or like motion tracking to control robotic arms, make designs like that, or directly manipulate how you can produce. But I actually think there's a huge void there to explore. So where you can still have the artistic freedom that's really nice in architecture. So not to get these building blocks that we've all torn down from the 60s and 70s, but that they have a personal touch, a human aspect to them. At the same time, I think it's smart to use computers for what they're good at really quickly showing us which things are feasible or technically possible or impossible. So I think there's space for both in that process. I definitely don't think the role of the architect is gone. I just think it's changing.
We have a question from Nicholas Savage. He says, the CNC arm assembly work looks cost prohibitive. When do you think these processes will become competitive enough for the typical lowest bidder tender process?
So actually they're really affordable. So all the projects we did are done with second-hand or third or fourth robots. So it's about, I don't know, between 5,000 and 15,000 euros, which for machining equipment is on the low end. On the other hand, a professional 3D concrete printing setup will set you back €500,000, so, or Canadian dollars. But then I actually think that the model that we use it in the middle of our street is one which is very interesting for more large scale applications. So where you find partners that are experts in their field and pull them into your project at the beginning. So you take those material and production constraints into account immediately and design with them in the room, so to speak. So I think that's the main lesson here, is that you that by taking those constraints into account in the beginning, you can really push the boundaries on those. And I mean, projects like Circular Experience, where we invested a lot of time in making that process work, where this robot is sawing and putting dowels. Those are projects that you probably won't see around a lot, because they are prohibitively expensive to develop. But that is what attracts more wealthy clients to those projects. So it's really dependent on the type of client and the type of project that you have, whether something is prohibitively expensive. Yeah.
We have one of the attendants making a note that, so standardization does have its potentials and advances, but only when used in small units, it can create variation and creativity, in their opinion. So they do want to ask, so in the case of using a software and developing housing, is there a danger of creating a large unit of standardization that can result in homogenization, leaving less or no room for creative variation?
Yes, there's the danger of that. So the tool that we make is really more like a three-dimensional Excel. So it's something that we give to people that are not trained, like architects or designers, to get an idea of what the spatial ramifications are of the demands that they put into a project. So if you want to have 700 units on a relatively small plot, that's going to create a huge volume there. So and it will cost a lot of money, of course. But then what I think is important to realize is that from these initial ideas that are stored in that configurator, you will go into a relatively traditional design process, although augmented with all of the information from the configurator and BIM, this whole BIM design library. But architects still have the freedom to turn that into a design that suits them, except that they cannot change those floor plans. And this is the thing that that happens in almost all of social housing projects, is that architects go on quite a tour to try and find a new super efficient floor plan. But at least in Holland, the demands on these are so stringent, and the cost, the allowed cost is so low that any project ends up at the same 10 floor plans. There's no, like in the past 20 years, there has been no change in that whatsoever. So in that sense, we want to skip that part of the design process and serve those on a platter, and then the architect can focus on what they do best, and that is to give shape to such a building in its context.
We have a question from Elsie. On the modular building concepts, do they, for example, the walls, ceiling panels, etc., allow for services such as electrical and mechanical? Are these installed after, or are these installed on site after the units are put together?
So the electrical, mechanical, and plumbing are installed in the modules in the assembly hall. So they're actually prefabricated by our partner, this installation company called Breman. So they so for example, for electrical, they make this whole spider of wires, this sort of wiring loom, like in a car, and then they put it in the factory, and the only thing that happens on site is that it's connected. So 90% of that, 99% of that work is done in the factory.
There might be, there is another question.
So Stephen is asking, do you believe that computational design in architecture and very possibly beyond will overtake and become the typical design process in offices, or will it remain a specialization in the industry?
I think it's a bit like being able to do renderings in a way, where I think it will be part of the regular design process. So where you used to just do renders at the end of the project by a specialized firm, now you use them in between your phases to show the client what you're up to, or you even use VR if you have a bigger firm or room for it. But I think in that sense, it will become part of the usual workflow for architecture firms. But at the same time, I do think you can really design much more efficient or expressive buildings if you really embrace what a computer can do in that sense. But that requires really different skills than are now available within an architecture firm. So you can see that certain software suppliers are working on that, like Autodesk is making generative design software, but those tools are still at a place where they're mostly used for very geometrically complex designs or just to do floor planning. And so they're really focused on these areas where you can now apply them, and they're not really good general use tools in that sense. So I think there's still quite a long way to go to turn these into intuitive methods of working. So it'll probably take some time before it will become completely mainstream. But just to add to it, it's not just complex geometries like Zaha Hadid or generating a building for social housing. Like in pretty much any large project, there will be computational designers doing daylight optimizations or floor plan studies, climate simulation, these kinds of things. So there's already really a lot going on, but it's often not visible in the appearance of the building.
While we wait, there might be another question coming. I was wondering if you could talk a little more about circular design. You mentioned it, and you also had a diagram showing the kind of loop of maybe what you imagine happens to these buildings after they're no longer in use.
Yeah, so I think this is, you can see it in different industries. So you can see a lot of products these days you don't buy, but you lease. So the company producing them has an incentive to easily take them apart or easily repair them because they can then reuse it, or rent it out again. And even though the lifespan of a building is a lot longer, the same applies for these types of modular buildings. So we try to design them in a way that we can replace parts that are often replaced first. So a kitchen or a bathroom or a toilet is easier to replace than, for example, the load-bearing structure. That's pretty much impossible without disassembling the whole building. But for example, a facade, you can just take it off and put on a new facade without having to take apart the whole building. You can even do it while other tenants are still living there. And I think it's a sort of fundamental shift in how you think about a building as a sort of temporary store of materials, you know? So, and definitely, I don't know what the regulations are in Canada, but here in the EU, there's this CO2 tax that actually makes it very interesting to have these units coming in a couple of years that have already had their CO2 tax paid. So it means that they have had their environmental impact. They have no environmental impact to implement in a design, which can actually make them extremely attractive to put into a project. So from a commercial perspective, it's really a no-brainer to do. It's just that in the design of a building, I mean, we've been working on this system for 2.5 years, and now the first projects are going to be built with it. So it takes a lot more time to design a system like that, but it's also something that will be there for at least 20 or 30 years before you're getting it back. But I think what we see in Holland is that permitting takes a lot of time. Like getting a permit for a relatively large residential complex takes about 4 to 5 years, sometimes 7 years. and we have a housing problem now. So you have a lot of temporary housing going up, but this is of such low quality that we're now using our system as temporary housing, which is actually the quality of regular housing. But because we can take it apart again, they can use it in that situation and take it apart in 10 years. So it's, I think this housing crisis is really an accelerator for these kinds of developments.
I think that kind of leads to the next question. I mean, what you just described, like with circular design, requires more upfront planning. So that we have a question here. Does your design process include more time on ideation or schematic design? What is the role of computational design in our highly deadline-driven industry?
Yeah, it's really, it's more like a product development process really than a project project-driven process. So in a sense, there wasn't really a deadline to deliver on the project, except that because this system is so huge, you're designing 14 floor plans across 4 topologies, including facades, walkways, staircases, elevators, everything. So you're not designing one building, but you're designing the possibility to make 1,000 buildings. It is almost impossible. You cannot finish that. So you have to sort of solidify parts of the design and then work on something else and then iterate back onto the parts that you sort of already froze. So it's completely impossible to do that for one specific project and do it properly. So it's something I fundamentally believe in, is that we will go towards a much more integrated way of working, where you will get a logical sort of division between these systems. So a building which uses concrete will have more thermal comfort, will need probably a little bit less or a not so strong climate system for cooling or for heating, and will maybe need a little bit more sun shading, for example, but that these combinations of structure, installation, sun shading devices, that these things will sort of cluster, and that around these clusters sort of productized building systems will come up. And this will start in social housing, but and there will always be place for AAA architecture, you know, that will always be there. But I do think that you have to see this quite outside of the project by project process.
So we have Elsie, who would like to ask about the printed ceramic panels, which are amazing. So the first question is, are such printed ceramic panels suitable for exterior application?
Yeah, they're designed for outdoor applications. So actually the guys at RAP have now printed a facade for I think it's some luxury store in Amsterdam, which is outside, because it's glazed ceramics. So the products have all been tested. So they go into a weather chamber where they go through freeze and thaw cycles. They simulate like 40 years of bad weather. And so yeah, they're definitely applicable in that way. But yeah, it took a long time to get there.
And the second question as a follow-up is, has this process been used to reproduce ceramic panels for old historic building restoration work for interior and exterior?
No, not yet. Or no, it hasn't. It has been used to produce ceramic elements that are hard to make. So casting ceramics is quite an intensive process. So a lot of sort of roof tiling projects can be done in that way, but you do see that restoration, that really for restoration projects, that they're using more like sintered 3D printing techniques, so much higher resolution. So here you still have a layer of about 2 millimeters, and with sintering, it's like it's more accurate than the chiseled object you're replacing. So I think that's really a different. But there's a company. It's called Concrete with, instead of ET, 3D. That does this kind of stuff. They are also in the innovation doc that we were in, but they print things like for the restoration of some monuments in the Netherlands, but also they've done some projects on UNESCO sites. It's quite a good question. Yeah.
We have another question about the modular units. This attendee is asking, is heating and cooling individual to the modular units, or is it connected to a central system?
So the modules are designed in a way that they can do both. So there's space for building designs where they are controlled individually, but a lot of these inner city projects, because it's mostly mid-rise buildings, they're connected to what we call city heat. So it's sort of like a centrally provided heating system. So then they are connected to a central system. So this is one of those things that you have to take into account when designing something like this, that you leave a little bit of space within, for example, this utilities closet, that you can also make a connection to such a central heating or a shared heating supply. Because if you just dimension it on individual, then you will never get that anymore. So it's a good question. Yeah.
So we have a attendee noting very inspiring and innovative work. For the new Delft Blue project, would it be possible for artisans to sculpt the same product?
Yeah. Yes. Like if you would have a drawing, then you could do that. I think what I find actually more interesting about artisans is that they would do it slightly in their own way. So you would get something that has a bit of differentiation or a sort of a personal touch to it. But I think it's possible, but it's just financially not possible, and we don't have those artisans in the Netherlands. So I think that's to come back to that. I think what you can see is that there's a level of expression that becomes attainable again, although it was maybe attainable for really high-end projects, but that can now be applied in, let's say, middle of the market projects. Like we did a theater interior in Rotterdam, and I mean, we did that for the same price as that the regular acoustic cladding would cost. So I think this is the unique part if you combine design and manufacturing, is that you cut out a lot of steps in the process, and so a lot of margins for all of the people who have to manage and buy in and change and redraw, because you directly go from file to factory. It can really speed up and thus also reduce the price on these kinds of things. So it brings them within the range of the possible in that sense.
I'm not sure if we have any more questions coming. But we do have some notes in the chat. So we have Karita Garg noting, great presentation, inspiring work, thank you. As well as Elsie noting, thank you very much for a very informative and inspiring lecture. So just to relay those messages, I guess.
Thanks. Nice. Yeah, it was nice presenting. Like, and very good questions as well.
Perfect. So I think we're good to end off the session. I just wanted to thank the guests for your questions and comments, and from all the students, the faculty and the staff, we would like to thank you, Léon, for sharing your work with us. I think something that's really important out of all of this and the questions that came is how important it is to see all of this work outside of what we are working in. We can't fit it in the box that we're working in, like outside of the regime and the status quo. So it's very crucial as a reminder for us to have these conversations and how we can embrace unconventional design strategies to challenge 21st century architecture in the building industry. It's a very important moment globally to address the finite resources that we have around us and the impact that the built environment has on us and nature. So it's clear that we must look into other means, as Léon showed us, of design that can lead us who are involved in the industry to a more sustainable and equitable future for all. So thanks again.
Cool.
Cool. Thank you very much for that, Marwa. So I think we will wrap up. Thanks very much, Léon. That was really inspiring and quite interesting. I have more questions, but maybe I'll just catch you sometime. Maybe when we get to meet in person again, 3 years from now, when this is all over. So yeah, thank you very much for joining, and thanks also to everyone who's come to visit here in this virtual plaza that we've created. I would also like to thank the Department of Architectural Sciences staff, including Alexandra Bersanu and Leo Reutman, for their help, and also thank you very much to the students and members of our committee for their enthusiasm in planning today's lecture. And so just one final reminder for the next lecture, which will be on March 3rd, and we will be welcoming Eladia Smoke, Principal of Smoke Architects. And so I think that will be a very interesting lecture. So thank you again, everybody. Thank you very much, Léon. This is a great start to the lecture series this year. Hope to see you all next time.
Bye-bye.